Okay, the next talk is Network Lasso, Clustering and Optimization in Large-Scale Graphs. And the speaker is David Hallac from Stanford.
Hey guys, there you go, great. So thanks for coming out today. I'm David Hallac, and I'm going to be talking about some work that I've done recently with Jure, Leskovec, and Stephen Boyd. Yeah, I'm running into the same problem. So convex optimization in this day and age is everywhere. It builds control systems that keep airplanes in the sky. It does optimal sizing for circuit design, and everything in between. So let's say you're working on one of these applications. Perfect. So let's say you're working on one of these applications, and you need to build something that is solved by convex optimization. You're going to find that with convex optimization solvers, there's a trade-off between generality and scalability. On one hand, you could say, I want the simplest thing possible. I'm going to build something nice and simple, like use CVX. It's 10 lines of Python code. You have a prototype up and running in 5 minutes, and you've solved your problem. It works. It gets you the right answer. The problem is it doesn't scale at all. If you have a real-time constraint, if you have a large problem, without any structure or sparsity, a general solver will scale with the problem size cubed. So let's say you want to go to the other extreme. You say, I want to build a problem-specific solver. In this case, you hire an optimization PhD student. You give him a couple weeks, a fast computer, and he builds something, and it works perfectly. It's fast, it's efficient, it works great for your application. But you just spent a lot of time and money building this solver. And also, the reason it's so fast is that it's fine-tuned for this one specific problem. So if some new data comes in that turns out you have to change your setup, you might even have to start over from scratch. So we were thinking, sort of, how do you offset this trade-off and get something that's both general and scalable? So with these large problems that are too big for something like CVX, they can often be represented in a certain way, as a network. Now, what this overall problem is broken down to is a series of subproblems, which represent nodes in the network. Then the edges are the coupling or the relationships between the different parts of the problem. And as a result, when you sum them all together, the sum total leads to the original problem. Now, these networks can represent actual networks, things like transportation networks, power lines, phone lines, or they can be more representational networks, things like financial transactions, social networks, or even graphical models. So what I'm going to talk about in this talk is a class of problems defined on networks called the network lasso. What we did was we formally analyzed this problem, and then we developed a solver for it that can scale to pretty large problems while also being general enough that a lot of common applications can fall under this form. We're going to briefly look at a few, but the one we're going to focus on is predicting prices, housing prices, based on a series of regressors. So the network lasso is an instance of convex optimization, but a lot of well-studied, well-analyzed problems are actually instances of the network lasso. Things such as convex clustering, total variation, or fused lasso can be formulated as a specific network lasso problem. Then on the graphical model side, what we're doing is essentially Bayesian inference with latent clustering underneath. And a lot of the problems we look at can be written probabilistically, but those are just two different ways to think of a similar problem. So we're going to focus on the optimization view. There's a lot of related work, some specific papers on problems which are instances of the network lasso. There are people doing similar things to us, but from a graphical model standpoint, and also how we solve and scale our model is using these splitting and decomposition algorithms. So let's look at housing prices. You're given a set of regressors, number of bedrooms, number of bathrooms, square footage, and you want to predict the price that a house is going to sell for. The classic way, the way everyone's done in school, is linear regression. You formulate it as a least squares problem, and you solve for a set of weights that is going to be identical at every house, and you say each house's price that I'm going to estimate is just a linear combination of the weight times the feature value. The problem with linear regression is if any of you have ever bought a house, there are only three things that matter in the price, and they're location, location, and location. So what you don't want to do is say all houses I'm going to treat the same. I don't want to say all houses, if the same house is in the nicest part of town versus a dump on the other side, you don't want to predict the same price. So what you want to do is you want to cluster houses and say, I want houses to group together. And if you are sort of in the same cluster, in the same neighborhood, then it's fine if you use the same linear model. They are pretty much the same price because they're in the same area. But if they're, what you'll find is there's a trade-off here. If you say, I want these clusters or neighborhoods to be really big, then what you're doing is you're forcing houses which are truly really different to share the same model, which will mess up your results. But as you tune this the other direction and say, I want these clusters to be really small. Let's say to predict my house price, I'm just going to pick 2 houses down the street. Then there's not enough data. And I may have a very accurate model for these 3 houses, but there's really not enough information in these 3 houses to predict to build a good estimator. So this is where the network lasso comes in. I guess for some reason the image isn't popping up there. But what we do is we build a network where it's a network problem. Each house is connected to nearby houses with an edge weight of the inversely proportional to distance. And each house in this case is going to solve for its own regression parameters. So each house says, given my sale price and my regression parameters, I'm going to solve my own regression model. And then where the clustering or the neighborhoods come into play is the network lasso penalty. The penalty is going to say, if you're near another house, I want you guys to agree to a common model. And what this gets us and what this allows us to do is say that the data is going to be a data-driven way to finding neighborhoods, to finding clusters. It leads to very accurate and also very interpretable results. So let's look at some math now. What we're doing is we're solving for an optimization problem on a network. Each node I has a variable xi that we're solving for. It's an unknown variable that we're trying to optimize. Xi can be a scalar, it can be a vector, it can be anything. And what we're trying to minimize is the sum over all vertices of this node objective, fi of xi, plus lambda times the sum over all edges of wjk, the weight, times this edge objective. So what does it mean? First, let's focus on this node objective here. This is saying that each node I, we want to minimize fi of xi. Fi of xi is the convex cost function at node I. We already said that xi is the variable that node I is trying to solve for. In the housing example, these are the parameter weights, the regression weights to build the prediction model of the price. But in other examples, if you're looking at a control system, this could be optimal actions to undertake to enact some desired outcome in a control setting. The fi is the cost function. That says what exactly does the house want, or does the node want to minimize? In the housing example, it's how well the regression parameters fit the model. It's the difference between our predicted price and the actual price. In other examples, it could be expected loss. It could be fuel usage. There's a whole bunch of stuff. And going back before, this is saying any fi, any xi, it fits into this general framework where a node is trying to minimize something. Now, the edge objective says the edge between nodes j and k is going to have, first off, a weight, lambda wjk. W is just the edge weights that scales the relative importance. And lambda is a global parameter that says, how much do I care about this edge objective versus the node objective? And then what the edge objective itself is the L2 norm of xj minus xk. What that is saying is I want to minimize the difference between xj and xk. I want xj and xk to be as close to each other as possible. Now, this is what the network lasso is. It's the network lasso penalty, a generalization of the group lasso to a graph setting. First, it's important to note this is not Laplacian regularization. That would be if the L2 norm were squared, and that would try to smooth the entire graph and get a smooth answer. What we're instead doing is saying I don't just want xj to approximately equal xk. I want xj to exactly equal xk. So what this leads to is groups of nodes, nodes connected by edges saying I'm going to agree to the exact same model x. Xj is going to equal xk. And what we've done is we've clustered nodes on this graph into a set of different groups of nodes that share the same model. In the housing example, that's saying I'm going to find sets of houses or neighborhoods of houses which are going to share the exact same regression model, whereas houses in different clusters that have different x's are going to have different independent models. So what we're doing, it can be thought of as simultaneously optimizing something on a graph while clustering the graph into some interpretable result. This lambda term here is actually really interesting. It's a regularization parameter, and it allows us to, we pick the right value by things like cross-validation, but it has some really interesting properties along this path here. So in Lambda 0, that says the right-hand side goes away, and what each node does is it says, I want to minimize my own fi of xi. That's completely separable. You can solve it in one step. It's really easy. As you increase lambda, it says more and more nodes are going to be convinced or forced to agree to have their xj equal an xk of their neighbor. And as you keep tuning this lambda up, more and more nodes are going to bunch together and get the same model. Until finally, when lambda's large enough, there's a finite value lambda critical, it turns into something known as the consensus problem, which says I care so much about not breaking any edges that I'm going to come up with the single x that the entire network is going to share. And it's how can we find this single x that minimizes the sum of all nodes when they share this common x. So how we solve it, good thing we came after Mazir's talk because he did a great job talking about ADMM. As I mentioned, centralized solvers can't scale to the graphs of even a couple thousand nodes. So we need something more parallelizable or distributed. We use the ADMM alternating direction method of multipliers. And sparing the technical details here, it's parallelizable and it's scalable. And it depends on each component, each node and edge, solving its own subproblem. And then a series of iterative message passing across the graph to converge on an optimal solution. The trick is, because the problem is convex, we are guaranteed to get global optimality, and it's guaranteed to converge. And this is the truth for any convex fi and xi. That says no matter what application, no matter what I'm looking at, the same algorithm, the same ADMM-based algorithm will work. And it'll work fast enough for most applications. So we built a solver. It's available on our websites. And then we looked in two different dimensions how it does. First, we wanted to see how large problems can we solve. And then we looked what examples can we model, and how do we compare to common baselines. So first for scalability, this top graph here, the red dotted line is a centralized solution. This is a log-log plot that shows that it pretty much explodes beyond a certain threshold. And it's about problem size cubed that it scales. ADMM, there's a whole bunch of theoretical stuff, but you can see empirically it's slightly worse than linear. And as you get to large problems, this becomes orders and orders of magnitude faster than any centralized problem. Things that take minutes for us will take days or months or something for more centralized solutions. And then we said how large a problem can we solve? So we built a pretty simple network and solved for 100 million unknowns, and we were able to converge on a solution in about 14 minutes. So the takeaway here is for most applications, if you don't have a real-time constraint or some multi-billion unknown problem, this is fast enough for most of the things you need. So now going back to housing, we talked about how we're going to use the network Lasso to cluster houses into neighborhoods together. We compute the MSE on some test set, and we want to see how we do. So we're going to go back to this. We plot in this graph the regularization path, the thing we talked about before, and we're going to look at the two endpoints because they're really interesting. When lambda is really large, that brings us back to this consensus solution that says I'm going to build a common model for all houses. Now, if that sounds familiar, it is. It's linear regression. So the far right-hand side here says I'm going to build a common model and share it among all houses, and it does quite poorly. It has a MSE of 0.86. And then as lambda goes down, it allows houses to break apart. And the mean squared error goes way down, drops about 50%. Of course, as lambda goes too far, if you go to the other extreme and say, I'm going to ignore my neighbors, I'm only going to look at a very, very small neighborhood, then that says there's not enough information for each house. It only has itself and its nearby neighbors. So the MSE goes back up again. Though it is really interesting to note that the location-based, when lambda is 0, it can do something like, pick my closest neighbor and predict their price. And that actually does a lot better than something like linear regression just because location means so much. In this example, we're looking at Sacramento real estate in the Sacramento region. So how we can visualize and interpret this is plot heat maps. So when lambda is really small, what we're doing is we're plotting heat maps of the regression output, the regression variables. And the key is that if they have the same color, that means they share a common model. So when lambda is really small, each house sort of builds pretty much its own model with like a little bit of input from its neighbors. And more or less, they have similar models, but there is a lot of noise. And this lot of noise leads to a sort of small errors building up over time. As you increase lambda more, houses will start to cluster together. And you can see here, they're starting to form little neighborhoods. The MSE is going way down, and these neighborhoods are beginning to form. As you keep going, With Lambda's 10, this is an awesome picture. It's very interpretable, and it also has a tiny errors, meaning these leads to great predictions. So what this is saying is, in the Sacramento region, this is sort of what the housing neighborhoods look like. Some houses grouped together. There's different clusters if you look, and if you're into real estate in this area, it's actually really interesting. But the key is that what we said is we're not going to sort of enforce different clusters. We're not going to make different houses agree with each other. We're going to do a data-driven way to say we formulate it as a convex problem and say, how do you find your own clusters? And this leads to really good results and really interpretable results that you can see, for example, on the left-hand side, the entire city, the urban area has a similar model. And as you move right there are different models. It's actually a more expensive model in this case as you move to the suburbs. So it's a really cool result and really interesting with great results. Of course, as you turn Lambda even higher, it says, I'm going to force houses to come together even when they shouldn't come together, even when they shouldn't agree on a common model. So here, this is saying, houses which are in reality quite different are being forced to come to consensus, and the results start getting worse. And as you keep tuning Lambda up, what eventually happens is the entire graph is going to turn one single color. And that single color is the linear regression model when you just come up with unique common weights for everything. So in the interest of time, we can't dive into the other two applications, but what we looked at was two additional types of problems that you can formulate the exact same way. First off, we do event detection in time series data. We say we had a bunch of entry and exit data from UC Irvine and then a list of 30 official events that happened. And what we do is we cluster different times together. And if a group of times like that breaks off, we say that is an anomalous amount of traffic or anomalously positive amount of traffic. And that is what we consider an event. And we compare it to Poisson baselines and actually outperform some pretty powerful stuff. And then the other example is really interesting. It's network-enhanced classification. You can imagine if you're Facebook and you're trying to, let's say, predict music recommendations for people on Facebook. If you use Spotify or Pandora, most people have only voted on a handful of songs. So not enough information for each user to get accurate predictions of exactly how they'll like new songs coming in. But what you can do is say, I'm going to use my location in the graph. If all of my friends like R&B music, maybe I like R&B music. If all of my friends like country music, maybe I'll like country music. And what this does is it says, I'm going to cluster people sort of in the friendship graph of Facebook and find out exactly what type of taste in music they have. And what you're doing is you're sharing additional information from these neighbors in the network and your location in the network. And again, we outperform a bunch of baselines and lead to really cool stuff. So to wrap up, we've formally analyzed something called the network lasso. We've defined it, and we've built this solver that is computationally scalable. And it allows us to leverage network data to solve large-scale optimization problems. Our solver is pretty fast, it's scalable, and it's robust, meaning that a whole bunch of different applications can fall under this framework. And the same setup can solve a variety of different problems. If you look here, we also looked at image denoising, financial modeling, and a whole bunch of other stuff, control systems. So thanks for listening. I'm happy to take any questions you have.
Have a time for,
I have a question. What's the difference between your model and the existing label propagation model? Because the generality of label propagation also add a constraint to the penalty cost to allow the neighbor to be as similar as possible.
So that's a great question. They're somewhat similar. We talk about this in the paper, in the related work section. It's essentially what we're doing is we allow sort of a lot of fine-tuning, especially with this regularization parameter here. We say, we gloss over a lot of the details here, but essentially this whole algorithm from start to finish allows you to pick, for example, the right lambda. And a lot of the label propagation things are sort of more static, and we sort of wanted an all-in-one package that this solver that we built on our websites allows you to do. It's you plug in the problem, and it sort of abstracts away a lot of the ugly details and finds the right model, the right clusters, the right everything.
Great. Let's thank the speaker. Thank you, David.